Okay, so last time we talked about one way of thinking about quantization, with basically the idea of you have a symplectic manifold, you think of the functions on it as properties you can observe in your physical system, measurements you can make, and you pass mechanics by turning that algebra of observables into a non-commutative algebra. And thinking of states in quantum mechanics as functions on that algebra, basically sending an observable, or sorry, an operator to its expectation value. And of course, you can formulate all of quantum mechanics in that form. That's not usually what you'll see people do in quantum mechanics. Instead, they try to construct a Hilbert space and think of the operators as actual operators on that Hilbert space. The names you'll sometimes hear applied to these are that the approach purely thinking in terms of operators as an abstract thing is sometimes ascribed to Heisenberg, and realizing things in terms of action on a Hilbert space to Schrödinger, but there's sort of a lot of names you can throw around, and people were very confused about quantum mechanics for a very long time. Some of us still are. And so a lot of ideas got introduced in one form, and then it took quite a while before people said, oh, no, actually, you should think about it this way. All right. So the kind of classic example, but always a really good one to keep in mind, is you have a free particle moving on a line. And, well, if I were in classical mechanics, I would just say this particle has a position, it has a momentum. If you take a quantum mechanics class, you'll learn instead what you should do is you should describe it as a complex valued function on the line. And that every such function, so when I write L2 of R, I'm always going to take function spaces with complex values. So this is L2 of R mapping into C. I'm taking complex valued real functions, which are square integrable. Those describe states that your particle could be in. And the way that you see now the position and momentum operators, that they act on those states, the position operator by multiplying by just the function of x, the function of position, and momentum by taking derivative and then multiplying by minus I h bar. Oh, these factors of minus I h bar, they drive me nuts. And it's particularly bad because a lot of mathematicians decide, oh, these factors of h bar, they're just dumb, I'm going to get rid of them. So if you read sources that are written by mathematicians, quite a bit of the time the h bars aren't there, which just makes it harder if you're trying to write the version with them included. Oops. Sorry. Okay. So you'll note here, we've been talking all this time about symplectic geometry. And from the perspective of symplectic geometry, position and momentum are the same. They're both just observables on phase space. They have some Poisson bracket between them, but there's even a symplectomorphism of phase space to itself that swaps them. I need to send one of them to minus, but thinking about mechanics in terms of symplectic geometry, these guys are in a completely equal footing. So it looks pretty strange that when we go to this usual manifestation of quantum mechanics, they're somehow treated really differently. But they don't have to look that way. So quite famously, you can also describe quantum mechanics by doing Fourier transform on your wave function, right? Because it's L2 integrable, it has a Fourier transform. And Fourier transform exactly swaps the two operations of multiplication by the coordinate and taking derivative. So you can also write your wave function in momentum space as a function of the possible momenta, and So now the momentum operator will be multiplication by the coordinate function, which is momentum, and the position operator will be I h bar. Note I lost a minus sign there, not a huge deal. DDP of the Fourier transform. So somehow quantum mechanics also sees that there's nothing really special difference between position and momentum, right? The kind of underlying mechanics does treat them the same. But writing things out, writing the Hilbert space, somehow seems to kind of force you to choose between them. This is a little mysterious about like why the kind of usual presentations of quantum mechanics have this weird asymmetry in them. So somehow getting this Hilbert space requires some kind of breaking symmetry. As you saw, if you looked at the website for the title of the lecture, the key issue here is we're trying to do geometric quantization. So that's a form of quantization which is different from star products. It tries to actually construct a Hilbert space. But as we see here, it can't be a sort of totally canonical thing. There's no reason that describing the wave function in terms of position is better than describing it in terms of momentum. So we must have to be making some choices to get our hands on Hilbert space. All right, but the other thing I'll say is, I mean, these operators, they aren't totally shocking in their form from the perspective of symplectic geometry, because if I think of the phase space R2 as a symplectic manifold, then I can think of the function momentum as observable as a function, and I can construct its Hamiltonian vector field, and that's ddx. And similarly, I can do that with the position coordinate, and I get minus ddp. And so I look here, and up to a factor of minus h bar, I see that, well, position may be multiplication by a function, but momentum is differentiation with respect to the corresponding Hamiltonian vector field. And when I swap roles and I make momentum a multiplication operator, then the action of position is up to the scalar factor, the action of the Hamiltonian vector field. So there is something going on here in terms of symplectic geometry, some kind of hint of like, oh no, this is not totally bogus, but it's hard to think kind of systematically, what does this mean that we should do? Should we take the function? Should we take the Hamiltonian vector field? Well, as sometimes happens, the thing to do is to take both of them at once and then try to somehow fix things. So we can think about starting with a function f and constructing a differential operator, which is minus I h bar times the Hamiltonian vector field of f plus multiplication by f. That's a differential operator. All right, so that's a perfectly good differential operator. And, well, we want to think of this as some kind of operator version of the function, the observable f. Now, we run into a problem sort of right away, which is what happens when we take the commutator of two of these guys. Well, okay, we write things out, what how this commutator behaves. Now, the commutator of a function and a vector field as differential operators is the derivative of the function with respect to the vector field. So if you sort of go through what it means that we take the commutator of xf with g and of f with xg, both of those give you the Poisson bracket. And there's a factor of minus IH bar, but I pulled that out at the front here. So I've got the Poisson bracket twice coming from these guys. And then I have this term where I've taken the commutator of xf and xg, and I'm not going to simplify that yet. But if you're thinking about, these calculations we did with Hamiltonian vector fields, you should think, aha, that's the Hamiltonian vector field of the Poisson bracket. But if that were true, then our calculation wouldn't work out. So this is sort of pretty close to this operator when I apply it to the Poisson bracket with this extra term minus IH bar. But not quite, because I have this extra term of the Poisson bracket. So I would only get this working out if, instead of having that the commutator of the Hamiltonian vector field of F with the Hamiltonian vector field of G is, well, the Hamiltonian vector field of the Poisson bracket plus a correction term. And that correction term has to have the form 1 over IH bar Poisson bracket of F and G. That's what would kind of make everything cancel out and allow me to get rid of this question mark over the equal sign. Now, that's just not true if xf and xg are if you interpret that as the usual directional derivative on functions. But of course, vector fields can act on something else. They can act as covariant derivative on the sections of any vector bundle with a connection. So if that connection isn't flat, then it won't be true that the covariant derivative of the commutator of the covariant derivatives is equal to the covariant derivative of the Lie bracket of the two vector fields. It'll be off by a correction term, which is exactly the curvature. All right. So the realm in which we're going to be able to fix this is to look at Hermitian line bundles. So vector bundles whose fibers are copies of C. They're C vector spaces that are one-dimensional. And the Hermitian part means that there's an inner product on the fiber. And such a vector bundle, I can get one, they're in canonical bijunction with U1 principal bundles. So if I have elements of U1, those act on C and they preserve the inner product and the complex vector space structure. So if I use gluing maps that lie in U1, then I can use that to glue together a Hermitian line bundle. And an important point that I definitely got myself a bit confused about, I'm always going to write U1 as R mod 2 pi z by the map A maps to E to the A, E to the IA. And I should just emphasize here, there are going to be factors of I appearing and disappearing. I think I got this correct, but a bunch of them end up getting absorbed into using this map. So we just have to be a little bit careful about this because, right, sort of secretly here, if I take the derivative of this map, there's a factor of I that shows up a bunch of places. And so I can sneak this factor of I here in front of the Poisson bracket into this guy. All right. So what we ultimately need is a vector bundle where the relation we get on sections is that So the curvature of a connection applied to the Hamiltonian vector field for F and the Hamiltonian vector field for G. That means take the covariant derivative for those two vector fields, compute the commutator of that as an operator on sections, and compare that with the covariant derivative with respect to the Lie bracket. And I want that to be equal to the symplectic form applied to XF and XG, which is, of course, another way of rewriting the Poisson bracket of F and G. Right, so this is by definition the Poisson bracket of F and G, but I'd rather write everything in terms of the vector fields. So I can just forget about my Hamiltonian vector fields and say that I want the curvature to be 1 over IH of omega. All right. So this is just kind of a general point to be careful. That factor of 1 over H bar, there are going to be these different sort of scalar factors that show up. And I just sort of want to emphasize, like, some of this actually just comes from the curvature isn't really a scalar valued 2 form. It's valued in the Lie algebra of S1, which is isomorphic to R or to IR, but not canonically. Right. So one of the sort of points about the I is, like, if you're thinking about U1 as a matrix group, its Lie algebra is matrices with imaginary entries. But when you identify that with R, you have to sneak in a factor of I many places. So in particular, when I write this formula for curvature that has an I in it, then I'm really thinking of this as in U1 is valued in the Lie algebra of U1, which I can identify with IR. Okay. So just be aware. That's sort of not as scary as you might think. All right, so I need to find a connection whose curvature is the symplectic form. And come on. If the symplectic form is exact, then this is easy to do. Then I can define the connection whose covariant derivative is the usual covariant derivative. You'll sometimes see people write this as like ddx. So this means, like, sorry, I skipped a thought here. And consider, I didn't give myself enough space. I can consider the trivial bundle. Let me just erase this and I'll try again. Consider the trivial bundle. So I'm defining a covariant derivative on just usual old functions. And I can define it trivial bundle. I'm going to let this guy 0 mean usual covariant derivative. I had to make it clear that I was talking about the trivial bundle before it made sense to say the usual covariant derivative. This is just the usual directional derivative of functions with respect to tangent vectors. So if I choose my covariant derivative to be this guy plus alpha, so that means when I take the covariant derivative with respect to a function f of with respect to the vector field X, then that's the usual Lie derivative of F with respect to X plus the pairing of this one form alpha with X. All right, so I'm changing what it means to differentiate a function. Oh, and I probably should have put my factor of IH bar in there. Okay, so if omega is exact, then I can just do this on the trivial vector bundle. But exactly looking at this, if I have a connection on a trivial bundle, its curvature is always exact. Right, so we calculated this when we were talking about this Yang-Mills stuff, that when I have a non-trivial connection on, or if I have any two connections on a given principal S1 bundle, they differ by some gauge transformation, and the difference between the connections as forms is the one form given by D of that gauge transformation. So if I have, since I have a connection on the trivial bundle given by the usual covariant derivative, whose curvature is 0, every other connection on there will have exact curvature. So if the de Rham cohomology class of omega is not 0, then can't use the trivial bundle. But there's a sort of cool theory, often called Churn theory, that actually tells us, given the symplectic form, looking at its de Rham cohomology class tells us how to construct a bundle that has a connection with that curvature. So one way to think about this is, well, let's say I did have a connection with the right curvature. I could choose a fine enough cover of my manifold such that the corresponding S1 bundle on each bit of the cover is trivial. And on each of these patches, because the bundle is trivial, and if I choose a trivialization, my connection takes on this form, the boring covariant derivative plus a one form theta I. Where, right, because I've chosen everything fine enough such that my bundle is trivial, omega is the connection of, is the curvature of a connection on this trivialized bundle. So on each of these patches, I can write my symplectic form as the exterior derivative of a one form. And as I said, this is one of these points where I've actually sucked this I into the isomorphism between Lie of S1 and R. All right. So I need to now think about how does my connection change under gauge transformation. And as we discussed, if I think about my gauge transformation as a function from M into S1, identifying S1 with R mod a discrete subgroup, I can compute its exterior derivative, and that's the change of the connection. So on our, we had our big manifold, we cut it up into smaller pieces, and we trivialized on each of those pieces. Well, that means I have a gluing gauge transformation on the overlap. Let me draw a picture. I've got UI, here I've got UJ, right? And my S1 bundle over each of these gets trivialized. One way to say that is I choose a section of the S1 bundle over U1, which I'm going to make the obvious section of the trivialized bundle. And I choose a different section over UI, right? So on the overlap, there's a gauge transformation that matches these guys, which I'll call, in this case, GJI. No, GIJ. So yeah, this is the, I have on the overlap, I have a bundle that I've trivialized in two different ways. So composing one trivialization with the other gives me an automorphism of the trivial bundle, the gauge transformation. All right. And so I have that theta I minus theta j is d of gij. And if we are a little more careful about how we choose our cover, we can always assume that this overlap is contractible. So I can actually think of this gij as having a lift into R, right? Right now, it's just a circle valued function. If my overlap wasn't simply connected, I might worry that I had some problem lifting this to R. But I can assume that this guy is contractible, in particular, simply connected, and so I can choose a lift. Now, what do we find out when we look at sort of the triple gluing of this lift? Well, d of it is 0, right? Oops. D of this sum is 0. Right? It's theta I minus theta j plus theta j minus theta k plus theta k minus theta I. So it's 0, but it also induces a trivial gauge transformation. So it has to be constant 2 pi z valued. And this is another point where I want you to watch out for the constants, right? If I were thinking about functions valued in the Lie algebra of S1, then I would have an invariant way of saying that. I could say it's a function that lies in the pre-image of the identity under the exponential map. That's sort of a canonical thing in terms of the Lie algebra. But I chose what size circle I wanted to identify U1 with. And because I chose that map so that 2 pi times the integers would be the kernel of my exponential map, I'm getting that this guy is in 2 pi times the integers. All right. So this guy is actually a Czech cocycle that represents the cohomology class of the symplectic form divided by h bar. And this is one of these points where I don't know if I want how deep I want to get into sort of cohomology. But we've talked about de Rham cohomology. There's another way of constructing cohomology groups where instead of looking at the exterior forms, you look at R-valued functions from your manifold into R, and the sum of all R-valued functions from your cover into R. There's a pullback map here. And then continuous functions from all overlaps into R, from all triple overlaps into R, etc. And this is what's called check cohomology. And this is actually another way of describing de Rham cohomology. If you take the cohomology of this complex, I think with this guy deleted, then you will also get the de Rham cohomology, but described in a very different way. And the reason that this is a good, and the equivalence you can kind of guess from this structure we have here, where on each of the UI, you can write your form as the derivative of something, and then you have some overlap, and you write the overlaps as exterior derivatives of things. The reason that this approach is nice is there's nothing special about R. So I can instead replace these with any abelian group. In particular, I can put 2 pi z. So this check approach allows me to think about cohomology valued in any abelian group. And in particular, this 2 pi z valued function on triple overlaps, so this is for each triple overlap, I have a function to 2 pi z. That represents this cohomology class of omega, precisely because I constructed it via this kind of, trying to take pre-images and failing kind of picture. All right. So what this is telling me is that if my symplectic form is going to be curvature, then it has to satisfy an integrality property, which just doesn't make sense in terms of de Rham cohomology, right? But when I think about it this check way, I can see this property I need. I need that the class of omega is 2 pi h z. And again, I'm warning you that, like, if you read this in different sources, you'll see factors of I show up because they didn't absorb it into their isomorphism, etc. And furthermore, if you think about this construction carefully, you can actually run this backwards, start with omega, and construct a circle bundle which has the right curvature. Right? You could start with omega, you can locally write it in terms of these thetas. You can then find a G that satisfies this equation. And that will give you a principal bundle that carries a curvature whose a connection whose curvature is a symplectic form. So it's a theorem of A that there's a complex Hermitian line bundle with a connection of the correct curvature if and only if the symplectic form satisfies this integrality property. And such a line bundle is called the pre-quantization line bundle. So, yeah. The whole point of this is now, if omega satisfies this integrality, then we can construct this pre-quantum line bundle. And now I can construct operators by taking multiplication function. That's a perfectly good operation on sections of this line bundle. And minus I h bar times this covariant derivative, also perfectly good operator on sections of this line bundle. And because of this curvature calculation, I exactly get that the bracket of these two operators is I h bar times this operator for the Poisson bracket. And this sort of naturally acts on L2 sections of this line bundle. So because of the Hermitian property, there's a norm on sections of this line bundle given by looking at the square of the complex norm of the section integrated over the manifold. All right, you might look at this and say, okay, great, we're done. Right? We found non-commutative operators where the usual bracket matches Poisson bracket perfectly. Great. So we can all just go on. Not so much. So this is called the pre-quantization or pre-quantum Hilbert space. Why is it called pre? What's not quantum about it? The issue is you do not get a representation of the algebra of operators in your quantum mechanical system, right? So for each observable, you get an operator on something, but composing two of these operators and applying this construction to the product of observables gives you completely different things that have absolutely nothing to do with each other. That's maybe an exaggeration, but like you don't get something which has the correct classical limit. You get something way too big. So how do we fix? In particular, I should mention, right, if we put into this if we put in R2n with the usual symplectic form, which I'll just remind you, the tautological symplectic form is exact, well, then we get L2 of R2n as our Hilbert space. And that's wrong. We wanted L2 of Rn. So this is no bueno. What we need to do is somehow get half as many directions, right? We got R2n here. We wanted L2 of Rn. We've got sort of too much stuff. We need to get rid of some of these things. So we need to somehow cut out half the directions. And our previous example with position and momentum spaces tells us we have to do that in a way that requires making some choices. So one way of doing this is what's called a real polarization. So we take our tangent bundle of our symplectic manifold and we choose an integrable Lagrangian subbundle. So a smoothly varying choice of the Lagrangian submanifold at each point, and which is locally tangent to a foliation. This is what the integrable part tells me. And the rough idea then is that the Hilbert space should be the space of sections of my Hermitian line bundle, not all of them, only the ones that are covariantly constant for all vectors tangent to the polarization. So it should be constant along the leaves of the polarization. And this looks good. this sort of solves a bunch of our problems, right? Because if we apply this with the polarization of fixing the position in R2n and looking at the whole, all possible momenta, that gives me a Lagrangian subspace at each point. It actually gives me a nice Lagrangian foliation. So my polarization is the tangent spaces to that. And indeed, I get back half the size. So if I started with R2, I get L2 of R. My function can only depend on X, it can't depend on P. We have to be a little bit careful about this point because remember, we're taking things which are constant, not with respect to the usual connection on functions, but to a non-trivial one. In this particular case, I can take the usual covariant derivative minus 1 over I h bar p dx. And if I take the covariant derivative with respect to p for this connection, I get the same thing as the usual boring covariant derivative. And similarly, if I wanted to swap the roles of x and p and take the foliation given by holding p constant, well, then I would be wanting to look at the covariant derivative for ddx, and I can choose a different connection. I'll note here, these guys are related by the gauge transformation. So these are two different connections on the trivial bundle. They have to be related by a gauge transformation. And the right gauge transformation is the exponential of xp over I h bar. So for those of you who have thought about this stuff and think about Fourier transform, right, it's not surprising here that this is the kernel of Fourier transform that shows up. So I think, I don't think we're going to have much time to talk about this. I guess we'll see. But one of the kind of tricky things about this story is how does the answer depend on your polarization? Right here I said, okay, I can choose x constant, or I can choose p constant. And well, I get the two descriptions of Hilbert space I saw at the beginning, and I know those are equivalent because I can use Fourier transform to go between. And there is sort of a general theory about how to do this, which produces for you Fourier transform in this picture. And, I think about as much of a hint of that as we need is given by the appearance of this gauge transformation relating these two spaces.
Sorry, quick question.
Mm-hmm.
I just want to make sure I'm following this last piece. That when you say that you can choose this particular form of the connection, we're talking specifically about the case cotangent model of R here.
Yes.
Okay. So yes. Yeah. Okay. Just making sure.
Though I mean, extending to Rn is not hard. I mean, I think I'm going to do several things, mostly in the case of R2, but if you wanted to do them for Rn, you would just like add in indices everywhere and sum, right? Like.
Okay, but when you said that, when you write here that this connection, the trivial connection minus IH bar over PDX works, what is this connection that we have chosen here? This is a connection whose curvature,
right, whose curvature is equal to I over H bar times the symplectic form.
Okay, because I thought the connection was already fixed by the omega, or I guess it's only fixed up to gauge transformation, so we still can choose
exactly.
one. Okay, I see. All right, got it. Thanks.
Right. So I mean, yeah. Okay. The curvature here is H bar omega. Yeah. I mean, exactly what this is saying is that if I stuck with this original connection,
That's the connection that we defined earlier because PDX is the alpha, is the canonical form for the cosine.
Sure. And I look at the Q constant direction, then I would not get constant functions, right? So with respect to this guy, right, the covariant derivative of ddx is, let's actually apply this to a function.
Oh, I see what you're saying. So it's like, if we had chosen that for our connection, then the polarization would sort of be given, but like would have to be P equals constant.
Right. Well, no. I mean, it works perfectly fine, but the covariantly constant directions along the foliation for P constant are not functions that are independent of P. They're functions that have an exponential dependence on P. Which, you know, if you follow through what this differential equation tells you, right? This is exactly telling you that with respect to P, it varies like e to the minus IP. Yeah.
I see. Huh.
So, and one way to sort of see that in a slightly less calculation heavy way is to choose a different connection where it is just the boring constant functions, and then say, oh, well, they're going to be related by this gauge transformation, right? So, you know, multiplying by this scalar sends sections that are flat with respect to one of these connections, or parallel with respect to one of these connections, to sections that are parallel with the other one. And so, you know, for P constant, sorry, I said the wrong thing.
Yeah, no, I get what
so with this connection, it's functions that are independent of X. And with here, it's functions that depend on X by e to the minus IPX. Maybe I missed
yeah
H bar or something, right? This probably should have had an IH bar in it.
But basically, is it true that once we have fixed a choice of this connection, and then the polarization is sort of determined, like there's only going to be one choice that will, whose constant sections will be, okay, actually I don't even know exactly what we would.
No, that's I mean, as you say, the connection is unique up to gauge.
Yeah, but I mean, once we fix the specific connection.
And, you know, remember, if your bundle is non-trivial, it doesn't even make sense to ask, like, how does it compare with the sort of usual covariant derivative? Because there is no usual covariant derivative on non-trivial.
Yeah, no, I meant like, once we have chosen a connection, is the polarization determined?
No.
Okay.
You can use any connection with the polarization, right? And all you're going to do is like apply a unitary gauge transformation to the parallel sections.
Oh, okay.
So you're not changing what the underlying like Hilbert space is.
Okay. I better just let you talk.
Yeah, no problem. I'm happy to.
Can I ask like a question real quick? Like kind of a vague, big picture question.
Mm-hmm.
So like just thinking about like Euclidean space.
Mm-hmm.
So I guess oftentimes we think of like in the quantum, or we think of our in the quantum sense, we think of doing like a truncation of the whole system, where you end up with sort of like a discrete space, and you end up with like this this like finite like polygroup or something, like, and I'm wondering like, is like, does this stuff is there a way to like go through all of this stuff in like a algebraic geometry setting or something that like takes away all of the smoothness requirements, and like is there a way to go through this that like where you have this like truncation into like discrete, like starting in the classical setting, like does that, you know what I mean? Like
I know what you mean. I'm honestly not sure. Yeah, probably I would want to like see in a little more detail what you had in mind before I sort of said yes or no. Like I suspect this is one of these things where like, yes, you can kind of import the ideas, right? Ideas like taking derivative make perfect sense in algebraic geometry, even when you've sort of gone out of a context where you're like literally computing Newton quotients. But yeah, I don't want to, and you know, somehow, right, like in this particular example, a lot of stuff is like built on Fourier transform, and Fourier transform like makes perfect sense in other kind of group contexts. So I mean, this is somehow one of these things where I suspect, yes, there are other situations where you can import these ideas to, but probably it's a kind of case by case thing.
Okay.
So I'm happy to talk about individual situations. I also suspect there are people out there who've thought a lot more about this than I have. All right, it's already 50 past. Let's take a short break, and we can talk more about this when we're back. Did people come up with any questions while I was gone?
Yep. So I have a question. I guess I have two questions regarding just the existence of this polarization that we're doing. So I know, I guess on Kähler manifolds, what we can do is we can pick the, we want to do the holomorphic polarization where you just polarize out the anti-holomorphic parts of the fields. So that's kind of different from what we have here, right? The real and stuff. So I was just wondering, like, is there like what's the underlying theory that tells us, okay, when, for example, on a Poisson manifold, when can we have such an integrable polarization?
That's a really good question. I'm not sure I have a good answer to it. Because I don't think there is a very systematic theory, right? So there are sort of particular examples that people want to do. And yeah, I was going to get to more general polarizations in a minute. So, I mean, somehow this is, right, this is where one starts to say these things about, well, you know, quantization is an art, not a functor, right? So this isn't something where you should expect, you have a symplectic manifold and there's a machine, you just put it into and turn the crank, and out comes a nice polarization, for example. So there are many situations where these exist, but it's far from guaranteed. And then there's a lot of difficulties about the uniqueness of polarizations as well. Right. You know, you get the same answer when you choose different polarizations. And well, there are some approaches to that, which you can use in some cases, but there isn't a like, you know, nice, perfect sort of general statement of like, oh yes, always. So yeah, it makes life difficult.
I see.
So yeah, unfortunately, it's not a sort of totally clean theory.
Yeah, I guess that's something that one would hope to have.
It would be nice.
Yeah.
It would be nice. I suspect that's, I don't know, there's certain of these things that just everyone kind of acknowledges that they're hard.
I see. Okay. And I guess the second question is related to this. Like, for example, if we do symplectic reduction, are we guaranteed to also have a pre-quantum line bundle on the reduced space?
Well, definitely not, because
Yeah.
you can do symplectic reduction and get non-integral symplectic forms.
Mhm.
So, I mean, there, I think, you know, it's basically if you normalize correctly, then you will, when you do symplectic reduction at an integral point. So, so if we talk about the G invariant part of G dual, that's the dual of the Lie algebra of the center of the group, right? So if I have an actual map from the center of my group to S1, right, then the derivative of that lies inside the dual of the Lie algebra. And if I, I think I'm doing this right. Well, no, that's the wrong thing. Sorry, I don't want to think about it that way. I want to think about the fact that if I have a map from a character of my group, so a map from G to S1, or if I'm thinking about a complex group, I'll want C star. That gives me a point in here. And is basically in that situation when you expect to get a complex line bundle, like coming from an actual homomorphism like this. And the line bundle you get is the associated line bundle for the corresponding representation of G on C. Right? So I think that should be okay. Yeah. So that's the kind of picture you should expect.
Isn't there also a problem that if you have a polarization that you might not have any parallel sections? Like
there are tons of problems.
The leads are not simply connected or something. You could just have zero.
So many problems.
Okay. All right.
Yeah, I haven't even. I am planning to get to all of that stuff, but yeah, it's troublesome, and I mean, I admit this is not, my area of deepest expertise. So, I know enough to understand that these are problems and to understand some things about how you resolve them. But definitely it's not sort of something where I consider myself an expert. All right. Well, as we were discussing, sometimes you can't find a real polarization. Think about like S2. Right? That's perfectly good symplectic manifold. There's no way it could have a polarization because it has a non-zero Euler characteristic. Right? So, in many interesting situations, there's just no real polarization. And we can get sort of an interesting result by extending to the complexification. So a polarization on M, I'd said a real polarization before. So this is polarization with no, is a C-linear subbundle of the complexified tangent bundle, which is Lagrangian and integral. So real polarizations, of course, are examples of these, because I can just take the real polarization and tensor it with C. But on the other hand, if I have one of these which has sort of no real elements in it, so it has trivial intersection with its complex conjugate, which is the same as saying that it has trivial intersection with the actual tangent bundle inside the complexified one, then actually polarization is the same thing as the 0,1 piece of the tangent bundle for a Kähler structure on your manifold. So basically the integrability of the subbundle, we actually talked about this, right? The integrability of that subbundle exactly means that 0,1 vector fields are closed under taking Lie bracket, which we already saw was equivalent to it being an actual complex structure. And then being Lagrangian is the complex structure being compatible with the symplectic structure. Maybe I can actually write that in there. So, Lagrangian only if mu, omega, and j are compatible. And it's integrable if and only if on this complex structure. And that's exactly the definition of a Kähler manifold, having a complex structure, not almost complex, actually complex, and symplectic, which are compatible with each other. All right. So I say let HP denote elements of L2 which are invariant under the Lie derivative, or I shouldn't say Lie derivative, covariant derivative. For V, any section of my polarization. So any vector field which is parallel to the polarization. And this complex perspective is very useful because it lets us get polarizations in lots of situations where otherwise we couldn't find them. Right? So polarizations are very tricky to find on compact symplectic manifolds. Sometimes they exist, but they're pretty rare, and complex polarizations are much more common. So for example, if I take any symplectic 2 manifold, it has a compatible Kähler structure. And there's no reason, and it will only have real polarization if it's a torus. So this is just sort of one example. There's sort of many fewer things if you, many fewer possibilities for polarizations if you only restrict yourself to real ones. All right, the other thing is, even in situations where you have a real polarization, it can still be useful to have a complex one. So we can only quantize an observable in sort of the obvious naive way if its Hamiltonian flow preserves the polarization. So note, it doesn't have to send each leaf of the polarization to itself, but it has to send a leaf of the polarization to a leaf of the polarization. So for example, right, if I have R2 with, let's say, the vertical polarization, well, Hamiltonian flow with, so this is the X direction, this is the P direction. So Hamiltonian flow with respect to X is parallel to these guys, so that's okay. Hamiltonian flow with respect to P, well, it doesn't preserve the leaves, but it sends one leaf to another leaf. So that's okay. But on the other hand, if I rotate, I'm going to mess everything up. So if I take the function f equals x squared plus p squared, which is an important example of a Hamiltonian, it's the one for the harmonic oscillator, I'm going to completely mess up the horizontal or the vertical polarization. Right. So this is like the most common Hamiltonian you want to study, the sort of first one you want to make sure works. And well, it doesn't preserve either the horizontal or the vertical polarizations. This is not a totally insuperable problem, but I think it actually does sort of lead you to an interesting place. In particular, another one of these issues that Matthew pointed out is, well, you could say, wait a second, why don't I use the polarization by circles, right? Any one manifold and a two manifold is Lagrangian. So I have perfectly good polarization, which is just all the guys tangent to circles centered at the origin. So tangent to the level sets, x squared plus p squared equals. That really has a lot of difficulties though, because there's no continuous function other than the constant one with, no, not even the constant one, sorry, not other than the zero function that satisfies the polarization condition, because when I parallel transport around a circle, I get the exponential of a divided by I h bar. And if I were going to have a continuous function that was a parallel section, it has to be sent to itself by going around any of those circles, right? So I'm in real trouble. Now, there is a fix, which you can say, wait a second, L2, that's bigger than just continuous functions. There are things in L2 which are not continuous functions, which are like, delta functions, where you get closer and closer to all being supported on a circle. And there are things like that in L2, which are preserved by parallel transport. So like, this situation is savable, but it is complicated. On the other hand, I can also just remember that C is a Kähler manifold, and I can use its Kähler polarization. It's tempting to think, okay, I'm looking at things whose covariant derivative with respect to anti-holomorphic vector fields is 0. So if I were just thinking of functions with the usual connection, that would be holomorphic functions. But that's not quite right, because I do have this non-trivial curvature involved. There's sort of a natural choice for that connection, because I add 1/2 z dz bar minus z bar dz. I think I have this right. I apologize if there's some constant off here. This is closely related to the story we had before with x dp and p dx, etc. And so when you take covariant derivative with respect to ddz bar, so this is the complexified vector field that gives me the Cauchy-Riemann equations. Then derivative with respect to that becomes, maybe I should write this out a little more carefully, of f is df dz bar plus z over 2 times f. So you can work out that basically you can get rid of this annoying plus z bar over 2, z over 2 by taking f and multiplying it by e to the minus norm of z squared over 2. Take a covariant derivative with respect to this connection of that guy with respect to ddz bar, you get the usual derivative with respect to ddz bar times this Gaussian function. So the correct notion of the Hilbert space here is functions of the form f times this Gaussian, where f is holomorphic and the total integral of this, the norm squared of this function, is finite. So this is called the Bergman-Siegel space, or the Fock space, or the Bergman-Siegel Fock space, depending on who you talk to. I was reading some source that told me there's some long, complicated story where Bergman and Siegel were doing this separately, and they met at a conference, but they were doing different versions of it. And then Bergman got sick for a while, and then when he came back to it, he forgot about Siegel's talk, and so he started redoing all the stuff that Siegel had done. Apparently, people are very confused about exactly who should be cited with this, but it's a pretty cool idea. This Fock space, I mean, this is a Hilbert space that's separable, so it's isomorphic to L2, and it's isomorphic by a very nice function. I really hope I got this right. I'm now very worried that I screwed up I should put some constant here. But I think this is right. That if you think about, a lot of the formulas get complicated because people want to think about the holomorphic function instead of the one that's parallel for the connection. But if you write everything in terms of those, it becomes very nice. In particular, you can turn one of these functions into a wave function, one of the usual polarizations, by integrating over the fibers. And again, I don't feel 100% confident about this thing. I might have to insert some factors, but I think this is actually right, that I just integrate over the fibers. So I don't know. I actually only learned about this relatively recently. I think it's really cool. So if you have a wave function that's sort of normalized in the usual way, it's a unit vector in the space of states, then there's a corresponding Bergman-Siegel transform of it, which is the corresponding holomorphic times Gaussian function on C. And this is pretty cool because it gives you a function on the cotangent bundle, which is a probability distribution. And it's very tempting to think, oh, this is telling you the probability that your position is X and your momentum is P. And obviously that's insane because there is no such thing. Heisenberg tells you that. But it tells you that the probability that your function is roughly has that position and momentum. This one way to see how this kind of still respects Heisenberg, right, is that a holomorphic function can't become constant. It can't be compactly supported. So you actually have to have non-trivial support everywhere on C. But it's going to sort of decay as you go further out. But it just sort of, I don't know, I find this very interesting that you get this function on the whole cotangent bundle, and you get either the wave function in terms of position or the wave function in terms of probability by integrating over the fibers. And yeah, I'm running pretty low on time. So let me just say, like, the Hamiltonian quantizes really nicely in this case. X squared plus P squared is the same thing as Z times Z bar. And so it turns into Z times DDZ when you quantize. And then there's this extra half, which hopefully we'll have time to say something about. That might have to wait until next time. It's not so surprising because we're used to this Weyl quantization, but I haven't given you kind of a geometric explanation for it. And you get eigenvalues Hn plus 1/2. And maybe I'll just mention this should sort of remind you a little bit of this guy. Those are close to being the values of area, where you get trivial parallel transport around the circle and get a parallel section. But there's something a little bit off because it doesn't, the half isn't there when you do the parallel transport. Okay, so it seems like life is good and all our problems are solved. But in fact, their problems remain. In particular, I sort of skated pretty fast by exactly what space I wanted to take my sections in. Because I said elements of L2, which are constant along this polarization. Well, if you think about that for a minute, that's not going to work out very well, right? If I take a compactly supported function on Rn, and then I think of that as a function on T star Rn, well, that's not compactly supported anymore, and it's not an L2. If I extend it by just saying that it doesn't depend on the other n variables, that's very bad. So it's definitely not an L2. So how am I supposed to actually make this a Hilbert space? Well, you can say like, oh, you know, why are you making this hard? You just integrate over Rn instead of R2n, right? Like, you're thinking of it's a function on Rn anyways. Why are you trying to integrate over R2n? But the answer is because I want to start with a symplectic manifold. I don't want to start with, you know, something that's the cotangent bundle of. So for example, but even if it's a cotangent bundle, right? If I take T star of M with respect to the vertical polarization, then if I think that my wave functions are functions on M, how am I supposed to integrate those, right? Right, I can write down, this is something that actually makes sense, because if I'm integrating over all of, I made a bad choice. Sorry, M is always my symplectic manifold. So let me write this a little differently. If I take an arbitrary X and I look at T star of X, I have a volume form on T star of X, the Liouville volume form of the symplectic form. But I don't have a volume form on X itself. X is just a completely arbitrary manifold. I know literally nothing about it. So that's bad. It makes absolutely no sense to say that I'm going to take F and G to be functions from X to C, and then I'm going to integrate over X FDG. FG bar. I need a volume form here. But I chose my X to be totally random. X, you know, random manifolds don't come with a volume form. So what the hell is going on here? Well, I'm running out of time, so I guess we are going to have to talk about this next time. The thing we need to do is incorporate what's called the metaplectic correction. So in terms of T star M, that means that a wave function shouldn't be a function, should be something whose square is a volume form. Right? I need to be able to take this guy, multiply it by its complex conjugate. So really it's norm squared. It should be something we can integrate. So it should be a real valued top form. And the way to correct this is to take what's called a half form. So let me see. Well, let me say a little bit about this, and then we can discuss it in more detail next time. So the correct version of this is what's called a half form. And maybe I'll try to actually get into more detail about how we construct these next time. The basic idea is if I have any vector bundle, it has a top power, excuse me, and a half form is a section of some line bundle whose tensor square is that top wedge power. Now this is always possible for an oriented real vector bundle. Because for an oriented real vector bundle, you can, why is this? So if I have an oriented real vector bundle, then this top wedge power is a line bundle. And precisely because the vector bundle is oriented, you can assume it has positive transition functions. For some trivialization over a cover. So, I can take my underlying manifold M, I can write it as a union of open subsets. I can trivialize over the open subsets. And being orientable exactly means that I can choose my trivialization in an orientation preserving way on each of the open subsets. And so the transition function is positive real. So this minus 1/2 f is gotten by just taking the square root of those transition functions. And of course, we would be in trouble if I had any negative numbers or any complex numbers. But because I actually only have positive real numbers, I can do this in natural. And yeah, I think we'll talk about this more next time. You can describe all of this in terms of some double covers. And so metaplectic, where that name comes in, that's the name of the unique double cover of sp2nc. All right, so yeah, it's 2:30. Clearly, I'm not going to finish this before next time, so we'll just talk a little bit about this next time and then maybe move on to another topic. So there's only so much that can be said about it. All right, are there any questions? I didn't say this, but maybe I should. The point of taking this square root is then if you have two sections of the square root bundle and you multiply them, you get a section of the tensor square, which is exactly this top bundle. So this is a way you can make sense of the square root of a volume form. Two things you can multiply and get a volume form.
I mean, I guess you're going to talk about this, but like, what is there any general theory about when a line bundle has a square root?
Well, I just showed you over the reals that the answer is
When it's
yes, if it's orientable. And I think if you think this through, the answer will be no if it's not, because the square of the bundle. Over the complex numbers, you can think about this in terms of Churn theory, right? That you're going to have a square root if you're twice the if your curvature is 2 times an integral cohomology class.
Weird.
Yes, we'll talk about this next time. We'll actually have time to define this metaplectic stuff. Well, we'll see whether that's actually a good idea. All right. Any other questions?
Not really a question, but I just noticed this similarity between, like, for example, the Riemannian manifolds, and you have a metric, and that gives you a SL bundle structure, and then you do this double cover stuff, and then you get a spin bundle.
Yeah.
That's sort of similar to what we're doing here.
Yeah, I mean, it's yes, it's a similar story. I mean, there's sort of a general mathematical framework for finding, the idea of if you have a bundle, how do you extend that to a bundle over a central extension? Right? So you can phrase all of this in terms of, in order to get a square root, like you need to take your frame bundle and, change its structure group to be some central extension. So I'll at least say a little something about that next time.
Okay, thank you.
And also, I don't know too much about physics, but like, I know that there's sort of like bosons and fermions, right? And when you think about these wave functions, they're usually kind of this like one function thing is usually like just a boson, but when you go to fermions and you need to have spinners or something like that, right? So like, is there like a spinner version of this whole story where you have to take sections not of a line bundle, but of a spin bundle or something?
Boy, that's a good question. I don't know.
Huh. Okay.
Like you're absolutely right. But
Curious, yeah.
I don't have a good sense of that.
Okay.
All right. Any other questions? All right. Guess I'll end the call. All right. Everybody have a good Tuesday.